Okay, we are going to be looking at DC circuits today. That is the second big topic in our electricity unit. And let's get going here. Okay, open up your notes to page 2, and it says Ohm's law at the top. Okay, so everything kind of revolves around Ohm's law, which is a mathematical relationship among electric current, also known as amperes or amps. I'm sure you've heard amps before. The resistance, ohm, which is called ohms, and voltage, which you know of as volts. It was named after the German scientist Georg Simon Ohm. In direct current circuits, or abbreviated, you'll see DC circuits, Ohm's law is simple and linear, which means it's a straight line. Electricity follows a straight path. And the equation is such. V equals I times R. So on your page there, you can fill in the blanks with the different variables. I stands for the electric current, or amperes, or amps. R is for resistance. And V for voltage. Okay, so far so good. Here we go. Now, what do all these new terms mean? Okay. Current, so that's the first one. So the amount of charge passing a point in a conductor every second. That's what the current relates to. Okay, it's measured in amps. It's named after a French physicist, André, why did I get all fancy there? André Marie Ampere, hence amps or amperes. We can use an ammeter to measure the current of a circuit, okay, just like we did at our station with the power supply. And if we look here, this normally tells you if it's an ammeter or a voltmeter. If it was a voltmeter, it would have a little V here, okay? And we have our different nodes connected on both sides, so the current can pass through it, and then as it does so, the needle will tell us how many amps, okay? So that's current. Okay. Sometimes we describe water flowing in a stream as a current, right? Like, oh, don't step into that, the brook, the current is way too fast. Okay. Which do you think has more current? So here we have two pictures, A and B. Which one do you think has more current? If you said A has a greater volume of water passing through, which means it has a greater current compared to B. Okay, so if you said A, that's right. It has more water passing through one point. So if you just put a point on that brook and watched how much water passed through, more water would go through there than if you picked one point on picture B. Okay? Same thing as current flowing through a circuit. Okay, now what is resistance? Oh, I'm sorry. I have the notes in the wrong order. So just turn the page and we'll go to resistance and then we'll come back. Okay, so resistance slows down the flow of electrons and transforms electrical energy into other forms of energy, which makes sense. Resistance, when you resist something, okay, you're not interested in it, it slows you down, okay? It's measured in ohms, and that's that cool symbol for ohms, okay? Little horseshoe looking thing. And it's named after the German physicist Georg Ohm. And the larger the resistance, the lower the current. Okay? So the more resistance, the lower the current. Okay? Which makes sense. Okay, if we were in that brook and we piled a bunch of boulders in where we were watching, we would lower the amount of water that could go through. Oh, they're going to let me erase this here. There we go. So if you look at the little picture there, it has a guy and he's holding like these two tubes, and the tube on the left has less resistance, which means that more current is able to pass through, right? So look at the number of marbles that are able to fall out of his tube, because the diameter of the tube is way wider than this one, which has a higher resistance, okay? So therefore less marbles are able to go through. Okay, and then we'll go back one page, back to our first page there. Okay, so voltage is the difference in potential energy per unit of charge between 2 points in a circuit. Okay, so what's the difference in charge from point A to point B? When you increase the voltage, you increase the current. So it's a direct relationship. Resistance was an inverse relationship, and voltage is a direct relationship. So if you take a look at this picture of this woman, she's holding two tubes, right? And on the one on the left, okay, her tube is level, okay, and so the same amount of voltage or marbles is passing out of both ends of the tube. But when you increase the voltage, okay, look how she tips the tube. Notice how many marbles come out now, okay? There's way more voltage, okay, in the second picture. Okay, what do all these new terms mean? Now I'm going to give you an example. This is how I think about it in my house, how I kind of put it all together. Okay, volts are similar to the pressure your hot water tank uses to push water through your pipes. But here it's to push electrons through a circuit. Okay, amps are like the flow of water. Okay, but really the flow of electrons. Okay, and your tap is like the resistor. Depending on how much you open your tap will determine how quickly the water falls through. So each resistor, hence the word resist in the same name, will allow electrons to flow through at different rates. Okay? So if you have lots of pressure, okay, lots of pushing the water through or pushing the electrons through, you have a lot of volts. Okay? And the flow of the water is our amps, and then the resistor, okay, determines how quickly the electrons or the water flows through the circuit or that one point. So for example, a light bulb or a noise machine or something like that, or a motor, okay? I like this picture. Okay, so see, here's ohms, okay? Here's the volt, so he's pushing, right? And then the ohms, right? Blah, 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 blah. Okay, this is the resistor. Okay, it slows down how many electrons are going through. And the amps is the flow of the water. So here it goes right on. Oh, I like that picture. I forget about it all the time. Okay, so there are a few other terms that we need to know. Okay, and you're going to see in these notes, there's all these kind of light gray squares. Leave those squares for now. We're going to come back and fill those in after. They are just the shorthand symbols for each term. Okay, so we're going to draw the correct symbol on the left of the definition in the mini box provided once we're done all of our definitions. Okay, so first off is a battery. So this is a combination of electrochemical cells connected together. So we're on page 4, if you're not sure. The chemical energy separates at the positive and negative charges with positive and negative terminals. What you've seen in a battery, we have like our battery, okay, and it has, okay, this is our positive end, and this is our negative end, okay, or vice versa, okay. Electrons are pushed out of the negative end, okay, so they always go out of the negative side. So that's a battery, okay. The electric load is something that transforms electrical energy into other types of energy. So for example, a light bulb, a buzzer, a heater, a motor, okay? As soon as we attach that onto our circuit, we're able to take the electricity from the battery and change it into something else, okay? Another word you'll hear is an electrochemical cell. Okay, and this converts chemical energy into electrical energy stored in charges. So if you think of lithium batteries that are in your cell phones, right? We know lithium is very reactive. We do not know that yet. When we get to chemistry, I'm going to show you what happens when we put lithium in water, okay? It's super reactive. If you've ever seen Bear Grylls, he does this survival show, and he showed one time when he needed to make a fire, and he didn't have anything, but he had an old cell phone, and he cracked the battery. He cut the battery, and he added a little bit of water to it, and he got an instant explosion, and he was able to have a fire. And so lithium is very, very reactive, okay? So what this is able to do, an electrochemical cell is able to change the reactive energy of lithium into energy that we can use, which is pretty awesome, okay? Commonly called a battery or cells. So the word electrochemical cell is also the same thing as a battery, okay? Okay, next up, the switch. A switch lets you close a circuit and lets electrons flow, or open it and stop the flow. That's pretty much it, okay? Just like the light switch, right? If it's off, then you've opened up the circuit and electrons aren't able to flow. As soon as you turn your light switch on, it closes the circuit and electrons are able to flow, and then you've got light in your room. Power source. This supplies the voltage, okay? It's the pressure that will move the electrons in the circuit. Next up, conducting wire. Okay, this is a metal conductor that allows electrons to move freely through the circuit. Okay, and in our house, typically, or in most houses, typically the conducting wire is copper. Right on. If you take a look or you ask your mom and dad to show you, often to your hot water pipes are also made of copper. They conduct heat, and you can feel it if you touch them. They'll be warm, okay, or cold if it's the cold water. Okay, what are conductors? Objects that do not hold onto electrons, but rather move electrons freely through them. So, for example, metals like copper and aluminum and silver and gold and iron. Okay, as opposed to an insulator, which are objects that hold on to electrons tightly, stopping the flow of electrons. And we saw this at one of our static stations where we had set up a circle and we were testing to see which ones were the best conductors and which ones were the best electrons. Conductors and insulators, sorry, my bad. Okay, so things like rubber, eraser, PVC, glass, ceramic, plastic, those are all supposed to be really good insulators. Okay, what is a resistor? Okay, just like the name shows, resist, okay? So it's something that slows the flow of the electrical current or electrons in a circuit. It has a specific resistance, okay? So for example, 10 ohms. When electrons encounter resistors, some of the electrical energy is transferred into other forms of energy, like heat. And each resistor has a specific color band that tells you its resistance. Okay, so if you look here, here's an example of a resistor. Then you can see there's 1 band, 2 bands, 3 bands, 4 bands. Okay, they all have the same thing. 1, 2, 3. And notice how the 4th one is shiny. Okay, and I'll show you why. If you look at the bottom of your notes there, it tells you what those bands mean. Okay, so the first digit is a numeric value, and so is the second digit. And then the third one is what we multiply it by 10. Okay, so for example, here the first one is brown. That is 1, and then the orange is a second digit. That's 3, so that'd be 13 times 10 to the 2, because red is 2. And the accuracy, okay, for gold, this is gold, that's 5%. So within 5%, that's how much it's going to slow down the flow of electrons. Okay. And the last two are the ammeter and the voltmeter. Okay, whoops, back up. No. There we go. An ammeter measures the amps passing through a circuit, right? And we saw what it looked like in our little activity here, right? Kind of like this, okay? Or it'll have a V on it. And a voltmeter is measures something that measures volts, okay? Ammeter measures amps, voltmeter measures volts. Okay, now we're going to go back to our notes and we're going to add the symbol in the correct square. Okay, so the first one is a conducting wire. Okay, so if you go to page 5, on the left-hand side in that square box, you're just going to draw a straight line. Okay. Okay. The next one is the battery. Okay, so go back one page to page 4. And there are 3 types of batteries that you'll see. Okay, if you have a 1-cell battery, that means you have 1 pair with a shorter side and a longer side. Okay, if you have a 2-cell battery, look, you have 1 pair and then you have a second pair. Okay, short side, longer side. And for a 3-cell battery, well, I'm sure you guessed it, you have 3 sets. 1, 2, 3. Okay. And the small side is where the negative terminal is, and the tall side is the positive terminal. So when we draw these and we're drawing cells, we're always going to add the positive and negative side. So with the 2 side, then smaller side is here, so that's negative, and then this would be positive. Again, this would be our negative end, and this would be our positive end. Okay. A light bulb. Okay. So that would be on page 4 underneath that where it says electric load, and we wrote example, a light bulb. So that's what it kind of looks like. It's just you have your conducting wire that comes up to it, then you have your circle with a kind of loop-de-loop through it. So the light bulb is actually just this, okay, and the line on either side is the conducting wire. Okay. Then we have our switch. Okay, still on page 4, just the last square on page 4. Okay, so this is an open switch, so that means no electricity passes through. So no electrons pass. Okay, so the light would be off. Or a closed switch, okay, means electrons pass. Okay, and you always want to make sure you add these little dots here and they tell us that a switch is there. Otherwise, if there's no dots, it just looks like conducting wire. Okay. Okay, motor, still on page 4, go kind of up and to the right. Underneath electric load, there's a motor, and again, this is just the symbol for a motor is a circle with an M, and the lines on either side, those are just the conducting wire. Okay, a fuse we don't really use, and we're not talking about fuses, but we do talk about resistors. Okay, so if you go to page 5, in the bottom half of the page on the left-hand side is a box, and I like this one because you have your conducting wire, and then you have kind of like what it looks like on a heartbeat monitor, and this shows that you have a resistor. Okay. And then the last two are on page 6, the ammeter and the voltmeter. Again, very similar to the motor, but for an ammeter we have an A, and for a voltmeter we have a V. Okay, so far so good? I hope so. Okay, we're going to use all of these symbols and put them together when we start to draw stuff. Okay, so what makes up a circuit? There are 4 things, and this is really important. So put a star next to this. Okay, we really want to make sure we understand this so that we, when we're putting our own circuits together, we have all these parts. Okay, so the first thing we need is a source, and that's the source of electrical energy. Then we need a conductor, which is the path through which the electric current flows. Okay, so a source, a conductor. Then we need a load, which is the device that transforms electrical energy into other forms of energy. So this could be a motor or a light or a buzzer, okay? And fourth, we have a switch, which is the device that can turn the circuit on or off by simply opening and closing the circuit. So those are the 4 parts of the circuit. They're really important. Okay? Now, how do we draw these? Okay, I like this. Circuit diagrams. I love drawing these. Okay, are diagrams that use symbols to represent the different components of the circuit. Okay, there's every time you build a house and you have floor plans and the electrician is going to wire everything, he has to come and bring down the plans to get approved, and it uses all these symbols so that everybody can understand what is going to happen. Okay, and it's drawn in very specific ways, and we'll just learn some simple ones. Okay, it shows the complete pathway that allows electrons to flow. And it gives an organized representation of the actual circuit. Okay, because it might be that you have wires that curve around things, but when we draw things, they're always at right angles. Okay, so it's an organized representation of what's happening. Now, how to draw them? The first thing we do is we draw them using a ruler, okay? And if you don't have a ruler, a straight edge is fine, okay? But you definitely want something flat to be able to use to do this, okay? Make all your connecting wires and leads straight lines with right angle or 90-degree corners. Do not let conductors cross over one another. If that's what you have, then electrons are going to choose the shortest path possible, and you might have a short. Your finished drawing should be a rectangle or a square. Okay, let's try this out. Okay. For example, so here's a picture. Okay, we've got our battery, okay, our negative terminal, our positive terminal, okay, we have our wire that's connecting our 2 light bulbs. It goes to a switch. Notice how the switch is open, okay, that means the electrons aren't going to flow through, and then the conducting wire comes back to the battery. Okay, so how do we draw this? Well, here is our battery. So this is our negative and our positive. So just like here, our battery negative end is on the right-hand side, we would draw it all as well on the right-hand side, okay? Then we draw a rectangle, right? 90-degree corners, okay? And then we have our 2 light bulbs, another 90-degree corner, and then we have our switch, which is open, okay? Open switch, and then it goes back to our battery. Now, does it matter if you had this light bulb over here? No, it doesn't matter. Does it matter if you had this one over here? And this one over here, no, it doesn't matter. As long as your items follow the same path and the same organization as the picture you're drawing. Okay? So, your turn. I want you to draw the following circuits, and don't forget to use your ruler. Okay? So I want you to pause the video right now and try it out, and I'm going to draw it as well. Okay? This is not working out so well, so I'm trying to draw on this weird sketch pad. Okay, so here I'm going to have my battery. Okay, and then I have one light bulb. I would be using a ruler this whole time. I'm sorry that I have to freehand here a little bit because I don't have a ruler to use. Here's my switch, and it's closed. Okay, and then I have my second light bulb. Okay, so there you go. That's what this circuit would look like. And then we'd have the negative and the positive end. Okay, try circuit B. Again, pause first and then come back and check and see if your picture looks like mine. Some of you will ask, how do you know if it's, whoops, how do you know if it's one cell or two cells or three cells? Okay, if it doesn't say, you can use whatever cell you want. Typically, a larger one like that is 3 cells. Okay, but if it didn't say, then you're welcome to draw whatever kind of a cell you would like. Okay. Okay, so I hope yours looks like this. We have our battery, okay, we have the negative terminal on the right-hand side, an open switch, okay, and then our light bulb here, and then a rectangle with square corners that come all the way back to the beginning. Yeah, they're kind of fun, right? So there are two kinds of circuits that we are interested in. Okay, the first one is a series circuit. Okay, and this is a closed circuit. Okay, the current flows in one direction. Okay, on one path, kind of like blood through our body. Okay, the current or the amps through each load, like the light bulbs, is the same anywhere on the circuit. So if you had 5 light bulbs or 2 light bulbs, the amount of current would be the same, or the amps through each one would all be the same. Okay? And we're going to get some practice with this. And the total voltage is the sum of each load. So if you have a 9-volt battery and you had 9 light bulbs, each light bulb would get 1 volt. You'd add up all the volts, okay? You'd add up all the loads, and then that would equal your total voltage, for example. Okay? The more resistors you add to a series, the lower the amps that pass through each resistor. Okay, but it still gets the same amount of amps. So, for example, with that 9 light bulb example, if we had just 3 light bulbs and it was a 9-volt battery, then each light bulb would get 3 volts, way more than if we had 9 light bulbs on that circuit. The more resistors you add, each resistor gets a smaller amount of voltage, which totals the amount of volts the battery can provide. Oops, sorry. Well, that's all right. Okay, so now let's label the parts of the circuit below. Okay, so if we take a look at this, this is a simple series circuit. Okay, here we have our switch. Okay, here we have our load. Okay, which is a light bulb. Okay, here we have an ammeter. Okay, here we have our battery. Okay, and notice it's a 1-cell battery. And we also have our conducting wire. Okay, pretty cool. So it's 5 components to this circuit. Okay. Okay, so here's an analogy I like to help make sense of things. It's kind of like a single water slide. If each person is an electron, they have one path to follow. As they reach the top of the stairs, they have lots of energy, and when they go down the slide, they lose that energy until they climb the slide again. Okay, so we see this is the battery. Whoops, sorry. As they walk up the stairs, they're getting more energy. At the top of the stairs, they have tons of energy. As they go down the slide, they lose that energy, okay, until they come all the way back and then go back up the slide again. Okay, one path, no other paths that they can choose. Okay, so now pause. Draw a series circuit that contains one battery, a switch, a resistor, a light bulb, and an ammeter, and do it all in that order. Okay, so you can pause the video for a second and then come back and see if yours looks like mine. Okay. Hey, there we go. So hopefully yours looks like mine. Again, we're trying to use a straight edge, okay, to get 90-degree corners. Here's our switch. It didn't say if it was open or closed, so you decide, okay? Right on. Okay, the second type of circuits we want to look at is a parallel circuit, okay? And this is a closed circuit as well, okay? And here the current is divided into 2 or more paths. Each load, or light bulbs, gets the full voltage, but half of the amps. So here's an example of a series or a parallel circuit, okay? So we have the batteries taking one path here. Sorry, I apologize. We would be going this way because there's the negative. Okay, and then never mind. Oops. Ah. Sorry. Okay, and then the other path it would take is through this light bulb over here. Okay, all the way back to the light bulb. Okay, so there's 2 paths that it can take. The electrons follow the path of least resistance. Okay, they are very lazy. Okay, electrons will find the path that doesn't slow down their flow as much as possible. Electrons are racing through the circuit, and as they move through the battery at a fast pace, heat is given off, which can create a fire if there's nothing to slow down the flow. which is often you notice like when your cell phone's been on for a long time and you're charging it, or you're charging your laptop or your Chromebook, and there's like that box in the middle of the cable, and if it's sitting on your legs or near you, it gets really hot, right? If you remove one of the resistors and leave it open, the electrons will follow the only path available. So for example, okay, here's a parallel circuit. Here's our battery. Okay, here's it's closed. Okay, so the electrons are flowing out of the circuit. They're able to go through this light bulb, but the light bulb has been removed over here, so the electrons can't go through. Okay, so they're all going then to this battery. They're all going through that light bulb. If you remove the resistor and close the parallel circuit, you will cause a short or a fire. Okay, so here's our battery. The electrons can go both through this way and through this way. But if they go through the further path, they have to go through a light bulb, okay, which makes them have to work. And they don't like that so much. So they would much rather go through here where there's no load, and that's where you get a fire or a short. And we do not want a short. Do not want a short. Look, sad face, okay? Now, let's label all the parts of the parallel circuit. We have a switch. We have a battery. We have our loads. Okay, we have our conducting wire. Okay, I think I got everything. Yeah. Okay, so here's another analogy, kind of like the first one with the water park. People at this water park all climb the same stairs, but have 3 different ways to end up at the bottom of the pool. So they might come out here, or out here, or out here, but then they all follow the same path back to the top of the water slide where they do it all again. Okay. Okay, now I'd like you to draw a parallel circuit that contains 1 battery, a switch, and 3 light bulbs. So 1 for each path. Okay, so pause the video, try it, and then come and check and see if yours looks like mine. That did not work on this one. I'm trying. Okay. Okay, so please use a ruler. Don't freehand, okay? I'm not able to put my ruler down on this pad, and so it's not letting me do straight edges, okay? So now we are going to get some practice with this in class and on some cool apps. So thank you very much. Have a great day.